Hello friends, welcome to Tech AJ YouTube channel. Friends, in today's video we are going to discuss the Kubernetes storage in deep. Okay, so this is the episode 7 of Kubernetes 0 to Hero Mastery series. Okay, so here we will discuss how data move from line of code in a container to physical magnetic flash file or in data center. Maybe you can think like you are using cloud, okay, like AWS Azure, okay, but in actual data will be stored inside some data center. Okay, so if you are working in cloud or in if you are aware from the hybrid environment, then it's good. If you are not aware, then everything will be stored inside some data center. In AWS cloud term, you can see inside the availability zone. What is availability zone? Availability zone is just a physical data center. Okay, so here we will also track the complete Kubernetes storage input output path, like how data actually reads, okay, and how data write will happen, okay, at disk level. Okay, so first of all, these are the core concepts of Kubernetes storage. So Kubernetes storage are in two types in nature. First one is ephemeral, second one is the persistent storage. Okay, so as we know that our pods are itself ephemeral in nature, so the data that will be inside the pod will be also lost when pod will shut down or delete. Okay, so that's why there is a requirement of also persistent storage. But as per our requirement, Kubernetes provide mainly 4 types of storage. Okay, what is the nature of storage? First one is ephemeral, second one is the persistent storage. Okay, so and how many types of storage basically Kubernetes provide? First one is empty dir, second one is host path based storage, third one is the persistent volume, fourth one is the config map, by config map or secret. Okay, so if we use empty dir, then its lifetime will be the equivalent to the pod lifetime. Okay, like if our pod will get terminated or deleted, as we know that pod is ephemeral in nature. Okay, so they can die, so our data will empty dir. If we give data from or storage from by using empty dir, okay, empty directory, then it will simply lose the data. So what is the use case of here? Okay, like you can see that if you can have a question like if empty dir or empty directory data is equivalent to the pod lifespan, okay, or pod lifespan, okay, then why it's here? Okay, it's because there are some use cases where empty directory will be very useful, like for putting the cache the data that is used for the temporary processing. If you want scratch spaces, then in that case you use the empty directory. And what is the host path? So basically host path, here in host path case we will provide storage from the host itself. Okay, from host to pod. So its lifetime is basically equivalent to the node lifetime. If node will crash, then our data will lose. Okay, if our single pod will crash, then our data will not lose. But also there is a problem. Any pod, if you have multi-cluster environment, any pod can schedule on different node. Okay, so like if this node is full, then Kubernetes scheduler will schedule that pod to the different node. Okay, so here we will require one more level of solutions, like so that our same volume should be mounted to the same pod. Okay, that are also called as the stateful pods, you can say that. Okay, how we can create that we will see later in video. Okay, probably in next video when I will cover the complete practical. Here just I will demonstrate how we can use the empty dir, host path, persistent volume and config map. Okay, this is just for creating the concept. Okay, so it's basically useful for monitoring agent logging. Okay, like we are logging inside the host path /var log. Okay, so that our when our pod will got terminated, data will not loss. Okay, because it's inside the host path, but still if our complete node will fail, our data will loss. Okay, so still it's a single point of failure for data. Okay, so here to rescue from all this problem, like data is the most important thing in any organization right now. Okay, because data loss can create or cause multiple issues to organization. Okay, like if there is any bank or insurance organization, then if their data is extremely important, although for relational database they are using the different technology, but let's suppose if they are using the Kubernetes based environment or OpenShift based environment, so then in that case they have to maintain the data persistence. Okay, so not a single transaction data should be lost. So in that case what we can use, in that case we will use the persistent volume. Okay, so it's basically lifespan is independent to pod or node lifespan. Okay, also the cluster lifespan, because this data will completely store on the separate storage. Okay, that is independent to cluster itself. Okay, but to access those data we will require a cluster setup and the other setups. Okay, so here it's very useful for the stateful apps that uses some types of databases, like it may be Oracle database, PostgreSQL, MongoDB. In some cases if you are implementing the Kafka, MQ, then in that case we have to use this. Okay, and last and important one is the config map or secret. You can think why it's in storage section. Okay, because it's also stores some type of data. Okay, it's not a volume itself, but it stores the data, that's why it's here. Okay, so its lifetime is equivalent to pod, but that as data is written inside the config map secrets, so it's just a configuration file. Okay, that we can inject. Okay, on the pod that will come up at place of the dying pod. Okay, so here basically it's useful for injecting the files configuration. Okay, so it's mapped into the RAM or temporary file system. Okay, so for just a simple demo for MPTDIR host path and persistent volume, and also so config map I will show in my next video. Okay, so here just a simple lab setup you can use. If you have any type of practice lab, then you can practice that. Otherwise you can here use the killer coda. Okay, killer coda Kubernetes playground. Okay, so here we will just go here and log in with your Google account. Okay, so you will get a lab setup within a minute. Okay, so here I am not logging in. Okay, because I have already a cluster that is in my laptop. Okay, that is basically a 3-node cluster. So let's go here and create just a namespace for our volume lab. Okay, so that all things will be separate. We will keep in separate namespace. It's also a best practice. So here we have created the namespace volume lab. Okay, so all the volume related or storage related lab we will do inside this lab. Okay, so here also, so this is the first YAML file. Let me explain you. This API version is 1 kind will be gonna to pod, because we will create a pod resource here, object. Okay, it's basically object type. Pod is also resource. So metadata here I have given a name empty directory pod. Okay, so its name will be the empty dir pod. Namespace we will use volume lab, just we have created, and the specification are the containers, like name will be the writer, image we will use busybox image, and command here we are executing to store data like echo transient data inside data temp.txt. Okay, well what also here its volume mounts will be the inside the data mount point. Okay, so here volumes name is scratch volume and its a type is empty directory. Okay, so just you can copy paste this. So here case I already copied that. Okay, so that is the same code. So here you can see that. Okay, so let me apply to kubectl apply -f from file and specify the your specification name. kubectl apply -f empty dir space .ml and also specify the namespace. What was the namespace? Namespace was volume lab. Correct? Yes. So our empty dir pod is created. So here use the kubectl get pod and here use the namespace volume lab. Okay, so here our pod is running, you can see that. So for verifying that, okay, we will just go inside this, we will run the kubectl execute -n for volume space and namespace, and here we will go inside the empty dir pod and we will cat this file. Okay, data temp.txt. Okay, so here you can see that transient data is present here, but what will happen when our pod will terminate? When our pod will terminate, this data will go, or you can say simply this data is lost. So if let me try first, I will log in there. Okay, still execute. Okay, okay, there I think bash shell is not there. Okay, so busybox did not have bash shell. Okay, so here we already see that like data is there, okay, inside our pod. Okay, so here let me just, if we know that if we terminate this, then our data will loss. So let me kubectl delete or empty dir Okay, so obviously we are not able to access that. Okay, okay, so here we say that no resources found in volume namespace, and also if we execute the same command here, then we are not able to get that file because currently pod is itself not present here. So how we'll get the data? Okay, so it means it's not safe to use this empty directory for the storing the real data, actual data of our application or our data that should be persistent. Okay, so let me just go into the host path. So basically host path maps directly from the nodes file system into our pod. So this is usually used for a system level monitoring or logging. Okay, it's always avoid to use host path in production environment. Okay, or if you use, then we have to follow the some strict guidelines. Okay, so let me use this. So vi host path spec.ml. So enter, paste here. Here also same, but here you can see that what is the difference. Here we are using in volumes, inside the volumes we are giving a name node log directory. Okay, and host path here we are specifying the host. Let me try to log in there. So kubectl execute interactive namespace is volume lab, and pod name is obviously host path pod. Okay, and this time we will use the bin sh normal shell because bin bash is not there. So okay, so here we are inside this. So let me go into the mount points that we have created here. It's inside nodes, node logs. Okay, so here we can see that complete our host path / var log is mounted here. When we create any log file or any file here, then it will be visible to our host. Okay, and it is stored to our host also. And also here, as I warned you, so this is not the production ready practice. Because why? Because although I did not have access of this host path, okay, but here I am able to write by using the Kubernetes host path method. Let me show you. Let Saurabh Singh host path demo on TechEJ. Okay, so here let me give a name, text host path text test. Okay, dot log. So enter ls here. So here is the host path test.log. Yes, it's here. Okay, so it's visual. We have written from pod. Okay, because here we are inside the pod. Okay, okay, so this is our pod. Let me go into the terminal here. So ls here, inside the verilog, here we can see that our file should be present here. Host path test. Okay, so here host path test.log is present here. Let me try to read that. Host let me read by cat. Host path test.log, no such file or directory. Host path test. So obviously we are not able to read from here. It's saying cannot open, but no such file or directory. Why it's not detecting this? Here we are. Okay, so we are here. So first of all, let me cd to verilog because we have used the ls there. Okay, so present working. Okay, we are inside the verilog. Now let me tell. Okay, so Saurabh Singh host path demo on TechEJ. Okay, so here we are able to read that. So let me show you. Once we will delete this pod, so that file should be present there. Okay, because it's stored on our host. Okay, in my case this is the node 1. You can see that kubectl get pods -n, name is volume namespace is. Okay, so -o wide. So this is the same machine, node 1. Okay, so here you can see that we are testing on the node 1/var/log. Okay, so this is the host machine on which this pod is hosted. Okay, it means this pod is being created on node 1. So node 1/var/log is mounted inside the /node logs. That here we have specified the volume mount point here. Okay, you can see that here in our specs. So let me delete this pod. kubectl delete pod host path pod. Okay, so it's deleted. Wait for a few moments. Okay, so let me check kubectl get pods. Okay, it's in terminating state. Okay, I hope it will take some time. In few moments it will be get terminated. Okay, so it's terminated. Now let me check here, ls here. Okay, you can still see that host path test.log is here. Okay, because it's stored inside the host path /var/log. Okay, so as per specification that we have provided here, we can see that here our host path is /var/log. Okay, so everything that we will create inside our container or pod inside /node/logs will be stored inside the /var log. Okay, so it means it will store for permanent purpose, but it's also where its life cycle is equivalent to the node life cycle. If node will crash, then this data can also loss. Okay, so in that manner we can give the volumes by using this host path method to our containers or pods. Okay, so this was the concept of host path. Okay, use cases we already discussed. We can store the any like logs files here. Okay, and for testing purpose or development purpose you can fully utilize this because it's binded to complete host path. Okay, so in the most of the cases, lab environment, development environment, it's basically mostly used to store the data too. Okay, because it's permanent in nature, it's persistent in nature, but not resilient, not highly available. Like if our host will fail, then data will loss. Also, if our pod will schedule to different like in multi-cluster environment, if our pod will schedule to different node, then also it's not able to bind or read the data automatically. Okay, from here. So here it's generally avoided to store the actual data. It's generally used for the storing the logging data or any data that is temporary in nature. Okay, so most important part here we will go with the persistent volume. Okay, so it's independent to pod node, and also sometime here we use the third party storage, so it's also proof to cluster failures. Okay, so we'll go with PBs. So persistent volume, so it's basically used for the stateful apps like mostly databases. You can also use for the like Kafka and MQ based applications. Okay, so basically for database or any other stateful apps, data must survive both pods and node failures. This requires a persistent volume claim, and also will require a PB to claim that. Okay, because without PB, how you can claim the PBC? Or second method is you can configure the CSI driver. Okay, by SC storage class. Okay, so here we will use basically local path provisioner for manual PB. Okay, so here we will not going to create the automatic PBs. Okay, by some configurations, because this is my simple lab setup. So here we will just get the clear concept of PB and PBC. Okay, so first of all we need to create the PB. So for creating PB on my local system, so I will use this specification. Okay, YAML specification. So here I have specified storage class name to local storage. Okay, because I did not have any enterprise grade storage here currently. Okay, so here I am using the local storage. So you can read the specification. This is API version 1 kind, like object type is persistent volume, metadata name is dbpb. Okay, so it's basically label dbpb by which our PVC will claim this. Okay, specification capacity is the 1 GB, storage is 1 GB, volume mode is file system, access mode we will use read write once. Okay, although as per your storage class like NFS or object storage, or you can also specify the or self storage, you can specify the read write many too. Okay, so here read write once I have specified because database will require this read write once. And also when we are supplying with the block storage, then most of the case here our PV specification will be the read write once only. Okay, and one more option is possible here, that is read only many. Okay, It means multiple nodes can multiple pods can read that file at simultaneously. Okay, but here read write once, it means only one pod can claim this or bind this and perform the read write operation on that. And persistent volume claim policy is the return. Okay, storage class name is local storage. Okay, as we are going to use our local storage here, and host path from where it will store or create this disk is the home store of PB disk. If inside that it will create a directory, okay, for creating this DB PB. Okay, I hope you understood that. Further we will also explain in the when we will get the lab of deployment and stateful set. Okay, so there we will discuss in more depth about it, but this is for just a storage point of view concept. Okay, so here I have already this. Let me ls here. So I have that pb.yaml. Let me show that is the same YAML file that here that I on my GitHub. Okay, so this is the same that I told you. So let me kubectl apply -f and pb.yml. Okay, so it means yes, I already created this. Okay, so here we can also just execute this. Okay, complete till here. Okay, I already also have the same. So let me show you. So kubectl apply -f pvc. This is just for claiming those pb. So it's basically created. So let me check that kubectl get pbs, and also one more thing, get pb. These all are not the namespace bounded. Okay, so it's saying status is currently bounded. Okay, it's bounded with, it means from our pod. So here you can see that name or pb is present here, db pb 1 gigabit read write once only. Okay, and reclaim policy is retaining, status is bound, volume lab db pbc. Okay, it's claimed from the namespace volume lab db pbc, and the storage class is local storage. Okay, so these you might wonder why these are coming, because I have earlier created this for my MongoDB. Okay, that is basically a stateful app or database, so that will require in this manner. Okay, so we will discuss further it, but for the storage perspective, just go kubectl get pods, kubectl get pods hyphen. Okay, so kubectl get pods hyphen name is our volume lab. Okay, so it's running fine. Okay, let me check on which node it's running basically. Okay, so it's running on node 1. So here it's fine. Let me go through with this specification too, so that you have understanding of this. Here we are specifying the persistent volume claim option. It means we are claiming our earlier created persistent volume here. Okay, although in enterprise we don't need to create manually PBs, we already integrated by using the CSI driver of the storage. Then here we will just claim those. Okay, so behind the scene all PBs will be created automatically. Okay, so we will also discuss those concepts here. Okay, so for now, just like we have given a name dbpvc, namespace is volume lab. Okay, so it means our pod will be created inside the volume lab, and the specification and access mode is read write once. That is the same to that pb. Okay, here we have specified the option to the same options here we have specified, like storage class name local storage, sources request storage 1 GB. Okay, so in this manner we are telling like this specification should match to claim the volume. Okay, if this specification will not match with these specifications, okay, so our pod will get into binding state and it will not start, and because it's not able to claim that volume. So I can show you the same also to you. If you change any of the parameter, like if you want to claim the storage 2 GB and the same, then it will our code will just get stuck there. Okay, so that specification should match. Okay, so let me show you quickly by example, otherwise you will not get the point what I tried to say. So kubectl, basically let me delete this first, pvc.yaml, okay, so it's deleted. Now let me check. Okay, it's in terminating state. Look, it will terminate soon. Let's here VIPVC PersistentVolumeClaim.iml. okay, so let me try to claim the 2 GB of space here. Just going to the insert mode. Okay, so I am currently claiming the 2 GB of space, but we have created our PB with the 1 GB only. So what will happen? Just apply this to our namespace, or that is the basically volume lab. Otherwise it will create in our same default namespace. So let me kubectl get pb get ports. The name is volume lab, namespace is volume lab, kubectl. Okay, it's in pending state. Okay, so you can see that it's in pending state. So let me troubleshoot the logs quickly. Okay, kubectl describe port, kubectl describe db port, give the port, and also it's not in default namespace, so we have to specify the namespace name volume lab. Okay, describe. Okay, so it's saying failed scheduling, default scheduler. What's failing? 03 nodes are available, pod has unbounded immediate persistent volume claim, preemption 03 nodes are available, 3 preemption is not helpful for scheduling. Okay, so it's basically giving the pod has unbound immediate persistent volume claims. Okay, so it's basically claiming the volume immediately, but unable to claim that. Why? Because it's claiming 2 GB of volume. We can further go deeper inside the logs and we can check the logs. Okay, so but for now we know that why it's happening, because we have created the issue. Okay, so for resolving that, what we can do, just go there, vi. Also here all the parameters should match, not only this. Okay, so in that manner we can create the PVC. That PV will be right when we use it with the stateful sets. Okay, then that time we will see the real power of PB and PVC. Okay, so for now just this is the separately we have given storage by using the PB here. Just our application or port is claiming, container are just claiming this PB. Okay, it means all data stored inside that PB will be stored inside a separate disk, right? Basically separate PB. It may be come from storage, it may be come from the cloud storage, it may be come from physical storage. Okay, so the configuration and integration is basically happen by using the CSI drivers. Okay, so we will also discuss that point here. So for now just you can understand that here now we are keeping all our data on separate physical volume that also comes from by using either SAN zoning or by cloud network attachment. It might be the NFS based network storage, might be saved storage. Okay, so let me apply this. Now you will say that pending state will resolve. kubectl apply -f pvc.yml and also namespace is our namespace is volume length. Storage forbidden field cannot be less than previous values. Okay, fine. For this we cannot simply apply that. First of all, you need to delete that pod. Okay, name is equal to volume lab. Okay, so now we can create that. Okay, so it's able to create. Why it's this error basically we get? Because we earlier have specified the 2 GB in our spec. Okay, but that is not able to claim the PB. But right now just we have specified the 1 GB. We are trying to specify 1 GB. That's why it's giving the error here. You can see that limit nails, because some validation is happening. Okay, it's not means we can specify anything. Okay, behind the scene Kubernetes validator are validating the things. We'll also see how this validation work in Kubernetes. Okay, for now that's fine. Just see the pods is running or not. kubectl get pods. Okay, db pod is right now in pending state. Okay, so we need to also stop and delete this pod. kubectl delete pod db pod name is volume lab. Okay, now we will apply. Okay, why it's getting pending. Now here you will learn one more extra concept. Because let me show you. kubectl get pb. Here you can see that this pb capacity 1 GB, read write once access mode. Reclaim policy is to retain this. Okay, and current status is released. Okay, but here this db pod is not able to mount that pb. It's not able to claim that. Why? So let me show the logs quickly to you. Oh, sorry, description. kubectl describe pod db pod and namespace is volume lab. Okay, so it's saying immediate persistent volume claims fail. Okay, still it's failing. So we need to first we have to verify our claim. Is our claim is currently fine or not? Okay, so here it's saying yes. Basically here our claim description is the claim space is the correct. Okay, so now we have question why it's our pod is still in pending state and not able to claim that, and giving this error, immediate persistent volume claims failure. So what will be your answer? Just think that. Okay, so for that, here I have showed you something interesting here. Here you can see that its policy is set to retain. Okay, here its policy is set to retain. It means data will be not recycled when new pod will claim this. Okay, so once when we stopped our old pod and try to claim with the different pod, basically why claim is not happening? Here is saying immediate persistent volume claims fail because here our reclaim policy is to retain, not to the recycle. If we set the recycle, then it will automatically claim to our pods, but here we are not using any stateful sets. Okay, so here we said that there is a problem, we are not able to map that because it's contain the old pods data. Okay, because it's a persistent value, it's contain the old pod data, but right now it's don't know because our pod name is changed, so it's not basically able to claim that PV. Okay, so now what is the solution? The solution is the stateful set. We will see it in our next video, but for now if you want to claim that, then you have to delete this PV. Okay, and then you have to create either new PV. If you want to retain the data, then don't delete this. Okay, or we can attach it to it with the different methods, but I am not going to discuss here further in more deep because it's a part of separate part where we'll discuss with stateful set. Okay, so here for now just you see that our data is now persistent and keep stored in the physical value. So now if you have to claim that, then we can create a new physical volume, or if you want to create the same claim, then we have to delete the old data. Okay, so that is the concept of physical volume and PVC claim complete. Nutshell, life cycle, what you can do with PV and what you cannot do, where stateful set will come in picture. Okay, so let's move further. That is the concept of config map. This is also a separate part where when we discuss stateful set, then we will also discuss the config map to store the same MongoDB or any other database configuration information inside the config map and also inside the secrets. Okay, but for now just you can see that you can use this standard pod. We can call the config here, config maps and secrets here. So just here like PVC is like persistent volume claim is like the user is requested like I need 10 GB of SSD. Okay, from where SSD will come, it's not matter with the PVC. Okay, and there is also concept of SC storage class. Here we can define the provisioners, CSI driver specifications like for HP 3 bar storage, AWS CBS or IBM 370-100 storage. Okay, like any integration with the third party storage. Okay, so that we don't have to manually create these PVs. Like here we manually created the PVs to show the concept. Okay, how it works. But when we configure the storage class and do our configuration successfully, like CSI integration, CSI driver integration, then this we don't need to create and maintain the PV manually. It will automatically manage the PV. Okay, just we need to specify the persistent volume claim in our specifications. Also, this PVC should be managed by the stateful sets in most of the cases. Otherwise, we will get the same problem that I have already showed to you. Okay. So, like persistent volume, this is the ticket. It is the request by a user for storage. It defines size, like I want 50 GB that I showed you. Access mode, read write once, read write mounted for single node, read write many nodes can read write execute many nodes. Here nodes or pods can basically use that. Like read write many option can be used with the NFS, cluster or shape based storage. And I showed you the persistent volume. This is the resource. It is specific piece of storage in the cluster. It can be a LUN of our SP3, L3PAR, LPAR, Electra, or any IBM based storage, Hitachi based, any storage, NAS, it is. So, okay, and maybe it might be come with the ISKG RFC, okay, and AWS EBS volume, Azure volumes, or any local disk that I showed you, okay. Like here I have showed you the local disk. Why local disk for PBs? Because I don't have currently any LUN or AWS EBS, okay. Although if you are practicing the same in AWS, then you can use the EBS for the same lab setup. So storage class, it basically defines the profile of storage. Instead of manually creating PBs, the admin creates the storage class with a provisioner CSI driver. When a user creates a PVC, the storage class automatically creates the PVs that I already told you. So why persistent storage? That I already specified, because the ephemeral nature of the containers and pods. Okay. So problem was the like if pod stress is deleted, rescheduled on another node, its local file system, the writable layer is completely wiped. Okay, so that's why. So the persistent volume exists outside the life cycle of the pod and also life cycle of the node also. Here we decouple the storage from the compute resources. Okay, so because our storage will be on different place, and here our nodes are just claiming that. In that manner, we maintain the high availability of data like the movable disk. Okay, like we can mount our PVC can claim this for this pod 1, pod 2. If our pod will just dying and rebuilding, dying, warning, then this all things will be managed by the stateful sets. Okay. So you will get a clear concepts of all these problems resolution. For just here you can understand the basic concept of the Kubernetes storage. So you can think like 4 stages. The provisioning. This is where physical meets logical state. Like here we have provisioning. In provisioning, like creation, we have 2 types of provisioning: static provisioning and dynamic provisioning. Dynamic provisioning is the user cluster just PVC referencing the storage class. The CSI controller automatically triggers the Electra API. Like if we take the example of Electra, then it will trigger the Electra API to create the volume. Okay, so static provisioning, it means here just I show you I have created the manually persistent volume in my local disk, or it can be cut from the third party LUNs, but here you have to manage the PVs. Okay, here you have to manage the PVs that I showed you. But why Kubernetes exists here? To minimize our overhead. So why we will use the static provisioning? We will choose, we will go, and most of the cases in production we will use dynamic provisioning, where all things will be managed by the driver, CSI driver itself. Okay, container storage interface driver. Okay, so you can get that CSI driver specification. Like you have question like how I can create that, how I will integrate those like storage. Like if you take example of HP Electra storage, so just you can go on internet and search HP Electra 96 specific model name, also storage CSI driver for Kubernetes. You will get the bunch of YAMLs with all the required descriptions. Okay, here, so just go on the SPE website. Here I am taking just example of simple one enterprise grade storage. Okay, although you can based on your requirement, you can just visit on your website. Like it might be the Hitachi storage, might be the any other OEM storage. Also it might be the cloud based environment. Okay, so it's depend on your use cases. Just I will tell the complete process how you can create in real time if you are going in enterprise environment. So here you can see that it's a complete page is here, how it work with Kubernetes core component. So here you can see that EHP storage is managed by the REST APIs. Okay, so here we will expose the Elytra REST API. Okay, basically. So here let's suppose we are integrating the HP Elytra. Okay, so this is just beyond the lab setup. This is actually how we will do, how you will do in production. So here you can see that Kubernetes inside external component, Kubernetes SIG storage, Kubernetes core. Like here we have control plane, compute, kubelet, compute. Here from here we just create a PVC claim, then it will go to this component, and from here it will call to the REST API. Okay, that is basically in HP Elytra storage. So here it will basically go to the container request, will go API request, will REST API request will go to the container storage providers, and that already we don't have to do that. Just we have to do the integration part. Like here we have to spread the node driver registers, CSI provisioners, CSI attachers, CSI resizers, CSI snapshot. All this if you required it. Generally it's required in production. So how it will completely work, you can just go deeper inside that. Just I am showing you the core concept, how you can do that. You can if you will like go back here and search by the artifact URL. Okay, so here we'll directly can go on SP storage CSI driver releases here, and inside that we can get all the release source code that is required for your use cases. Okay, similarly if you are using OpenShift, it does not matter because OpenShift is also based on the same Kubernetes concepts. Okay, so nothing you have to test that, just you have to read in more deep as per your requirement, because enterprise requirement, enterprise is driven by the requirement. Okay, so not by the my basic concepts. Like just you might be you have to be aware from the all these concepts, all these things happen in production. Okay, if you will not walk through with that, then you will not get an idea. Now you will get an idea like how things will go in the enterprise environment. Okay, so here you can also have like AWS EBS based provisioners. Okay, all those things you can just go and search, you will get that. So it will use the data path like same. We can reclaim or claim those PVC claims or PVs by using the either manually, either using the automatically, yes, storage class. So what will be the PV life cycle? So PV basically life cycle is the four things will happen with the PV. Either it will be available, bound, release or fail. Just I showed you. Okay, like once we create a new PV was available, after that it's bounded or claimed and active, and after when our PVC is deleted, then it's going to release state. Okay, I have already shown you all these things. Just I am going to giving a brief idea to you. We have already seen the practically like here. Okay, so here we say that this is released. Why this is released? Because we have deleted the claim. Okay, and here also why these are in bound state, because their specs are still present or system. Okay, so here it might go into failed state also and available state. When we'll create the new PV, okay, then it will be in available state, available for claiming. Okay, but we don't have to think anything about when we are using the storage class. We don't have to go into deeper, but this is the basic concept that is basically working here. So also the CSI is the main thing here. When you will go in production, then everything will be done by mostly the CSI by using the storage classes. So historically storage code was inside the Kubernetes binary in a tree. Today we use CSI, which allows storage vendor like SP, Native, Dell, VMware to write drivers as plugins. There are three main components of the CSI: CSI controller, CSI node plugin, external provisioner. So CSI, what the CSI controller will do? It's basically run on the master node. It takes to the storage API to create delete volume and attach them to nodes that I already shown you on the SP website. Okay, what CSI node plugin will do? Basically, it's run on every worker node. It handles the mounting and formatting of the disk so the containers can see it. And what is the external provisioner? It basically watches for new PVC and tests the array to carve out a new line. Okay, so when it will attach, when a pod is scheduled to a node, the CSI container storage interface controller trigger the controller publish volume. Okay, this is equivalent to telling a SAN, like if you know aware from the SAN, then here we are just mapping this logical unit number to this host word wide number. Okay, so that it can, our pod can see the PV. Okay, attaching by the PV key. See how this attachment will come. This attachment will happen by using the physical persistent volume claim. So at node level it will mount, like now we have moved from the API to the Linux kernel on our worker node. So device identification, the kernel see the new SCSI devices or FC devices like Dev, STB or anything. It will format, if new volume, the kubelet will format it with the file system HT4, KFS, XFS, sorry. So I already know that every Linux node will run a component named kubelet. Okay, so who will do all the identification, formatting? These all things will happen with the coordination of the Linux kernel and kubelet. And then it will globally mount. The kubelet mounts the device to global directory and the host. Inside the /lib kubelet plugins Kubernetes IO SCSI PV name and global mount. Then it will bind mount. This is the magic of CRYO. Like here we using CRYO. Use a bind mount to map the host directory into the container's isolated mount namespace. And at block layer, once the app writes a file like eco-data-mnt-db.txt, the data starts its journey through the kernel. First VFS will come into picture like virtual file system, a common interface that translates the write system calls into file system specific instruction. And then it will write to page cache. The data is not written to diskette, it sits in RAM's dirty pages. This is why certain power loss can cause the data corruption, because if first it write to page caches, then it will write to the block devices, block layer. So the kernel break the file into blocks, usually 4 KB, but you can specify. Okay, if you know the deep concept of the Linux volumes. So it uses the input-output scheduler like deadline or MQ deadline to decide order of writes to maximize the efficiency. And the low level is the transport layer. Now the data leaves the node's RAM and travel across the wire. Here encapsulation will happen by using SCSI or FC. So basically SCSI blocks command are wrapped in TCP IP packet and command travel over dedicated latch signal in specialized fabric. Okay, it will be obviously it will be stored inside some MBNB, because this is the modern standard to store that. Okay, because it's also provides the near zero latency. And then it will go to the HBA, basically host bus adapter, that will basically in our physical servers. Okay, physical servers have the HBA cards. Okay, there the hardware card that uploads the processing of these packets, so the CPU does not show. And then at last the physical media. Finally the data arrives at storage, array, SP3 file, etc. or cloud SSD. Everything. Like here in cloud, if you are getting the SSD, then how you are getting the SSD? Actually behind the scenes some storage will be provisioned. Some hardware will be there. Some hardware will be there inside some data center. In storage language, in cloud language, you will say like I am using the availability zone. In this availability zone I am creating this elastic block storage, but at last where it will be stored some inside some data center. Okay, So this is the complete concept. Now it will store inside some SSD. It may be NVMe based or you can say that Nitro based storage. Okay, so the flash translation layer, the array controller decides which cells to write to at here in the form of voltage 0 and 1. So now we reached to the bit level 0 and 1 that I promised to you. Okay, I will go from the containers code to the bit level. Now we are inside the bit level. Okay, so now voltage level to store at 0 or 1, the controller pushes electrons into the floating gate transistor. Now it might be it's a single level cell. Okay, high voltage is 0, low voltage is 1. Now it uses the basically SSD uses this concept to store and retrieve the data. Okay, so multiple here TLC and QLC concept will be used. Okay, so multiple voltage level represent multiple bits, like is 8 levels for 3 bits. This is where bit rot happens. If the voltage leaks over time, the 1 can also become the 0, so we have to control the bit rot. Okay, so for that also already the SSD softwares, like SSD also have some small softwares, you can call it firmware. Okay, so they basically take care of this. So all these things happen behind the scene. Okay, but just as a Kubernetes administrator, you don't have control on these. You have control on the till the CSI driver. Okay, and behind the scene will be managed by the storage administrator, and then behind the scene will be managed by the data centers provider, and then all these things will happen. But you should have idea of all these things. Okay, so like if there will be the case of hard disk drive, then it will work in different manner. It might be you can store inside some other things. Okay, like you may be use the tape drives, so it will use the different technologies. Okay, so at low level technology will be different. Like here I have taken the example of HP Electra to show you how you can create all the things, like when you are using any enterprise environment. So let's take an example of HP Electra 9600. Okay, this is the enterprise grade storage that is mostly used in the enterprise environment. Okay, so I am taking just an example of this. Okay, it might be in your case this storage can change. So you have to scan the devices, like device will be shown mapped by the sign zoning, okay, to your nodes, basically worker nodes, because in Kubernetes master node always uses the local disk of nodes to store their configuration. That's why it's recommended to create a high availability cluster with the at least 3 master node or control planes, so that if our one control plane will fail, then it will not affect our complete cluster. Okay, so basically it's scan when our zoning will happen. The CSI driver basically attach phase Linux kernel or worker nodes see a new hardware signal FC frames or SKG packets. So device scan that the SKG subsystem create a block device file inside /dev SDB like this. If you work on the storage part at Linux side, then you I'm damn sure you are already aware from this concept. But if you are just like cloud-based admin, then these things are also being happen, but things will just bit change. Okay, so all thing like this will be done by your node, basically your host machine, Linux machine. Like device scan will happen, multipathing will be configured, partitioning, FC. Okay, all these things happen behind the scene. These all things will be managed by the cloud provider. You don't have to think about that if you are using the cloud. But if you are in on-premise or in hybrid environment, then you have to take care of this also, because these are the actual technology that are basically happening behind the scene. Okay, so all these things, like step A, the global mount will happen, the pod specific mount will happen in that manner, and the bind mount will, like this is where cryo takes over and starting the container. Basically container runtime is the cryo uses the mount system called with the ms bind flag. It projects the host folder from step B into the container mount namespace. the container. This look like the root directory or data. Put the kernel knows it's actually window into the host /var/lab/kubelet path. Okay, so now gRPC communication will take place. How this will start? They uses the gRPC over the Unix domain socket. Okay, so when we'll run the command -ctl get socket, then you will get this socket where run cryo. Basically this request include the mount point instructions. Okay, then symlinks and propagation will happen in Kubernetes. Many things like config map secret uses the symlink or atomic update. Under those, Kubernetes mounts a time space directory. Okay, like this. It then create a system link named data pointing to it. Finally, your file config.yaml is symlinked to data config.yaml. Why? Because when you update the config map, kubelet creates a new timestamp folder and changes the data symlink to point to the new one. This updates all the files inside the pod instantly without restarting the container. Okay, so if you use Elytra, then you can use this command, get this command to basically check the configuration like thing. But I am sure that you don't use that, but this concept is required if you are going to implement this Kubernetes storage deep dive concept into the on-premise environment. Then definitely this will be very useful for you. So you can go through with this my Git repo. You will get all the concept, although I am not going to more deep. Okay, because I have created this document for my production environment, that is basically Elytra 9600. Okay, so this repo will be helpful for me. Okay, so for now you basically get the idea like how these things will work. Like we can create the storage class here in that manner with the name like this, parameters, backend, provisioning type, performance policy, and also you can all this information will get from the specific website of your OEM, of storage OEM. Okay, like it might be HP, it might be NetApp, it might be Hitachi. Okay, anything. Okay, so here that is the thing. Okay, so most important command here for troubleshooting is the crysctl. Okay, so you can use this crysctl for troubleshooting here, but this crysctl will require the root access. Okay, for inspecting the pods, inspecting the storage environments. Okay, inspecting the any error where kubectl might be not work. Okay, so this is the complete concept of the Kubernetes storage. In next video we will see how we can use the stateful set and utilize the persistent volume claims, okay, and secrets, okay, to host our stateful set application like Mongo database. Okay, so thanks for this video. Thanks for watching this video. Okay, see you in next video.